Greetings to Dr. Shahlan and my fellow classmates. I'm from Group 9 and I'll be presenting on crystalline imperfections with my group. First of all, let me introduce my group members. First would be Estelin, second would be me, Titus, followed by Noratika, and finally Awis.
I will start first with grain boundaries. Grain boundaries is a type of linear defect. In real materials, crystals are not perfectly single crystal. They are made up of many small regions called grains. Each grain has a different atomic orientation. The grain boundary is the region that separates two grains with different orientation. Because the atomic arrangement at the grain boundary is irregular, this region affects the properties of the materials. Next, I will explain about the effect of grain boundaries. Grain boundaries block the movement of dislocation, which makes the material stronger and harder. When the grain size is smaller, the number of grain boundaries increases, and this feature increases the strength of the materials. However, grain boundaries can also reduce electrical conductivity and can act as sites for corrosion. In conclusion, grain boundaries play an important role in determining the mechanical and physical properties of materials.
Hello, my name is Awis. I will explain about twin boundaries. A twin boundary is a special type of grain boundary where the crystal lattice on one side is a mirror of the image of the other. The region between two twin boundaries is called a twin, and the formation process is known as twinning. Unlike random grain boundaries, atoms at the twin boundary are perfectly aligned, giving it low interfacial energy. Next, twin boundaries form mainly in two ways. First, annealing twins form during heat treatment, especially in FCC metals such as copper and aluminum, due to atomic rearrangement during grain growth. Second, mechanical twins form during plastic deformation, particularly at low temperatures or high strain rates. This type is common in BCC and HCP metals like magnesium. Lastly, in terms of deformation, twinning acts as a secondary mechanism when sleep is restricted. It reorients the crystal structure, allowing further sleep to occur. Although less common than sleep, twinning is essential for maintaining ductility, especially at low temperatures.
Alright, I'll be continuing on line defects. The line defects are distributed into two categories, mainly edge defects as well as screw defects. Now, I'll be touching on edge defects. Edge defects will be explained in three categories. The first would be extra half plane, Burgers vector, and finally motion or glide. For extra half plane, an extra plane half plane is a defect characterized by an extra partial plane of atoms inserted into a crystal lattice. The dislocation line is defined as the edge of this extra half plane. The lattice is then compressed above the line under tension below it. Now moving on to Burgers vector. Burgers vector is the magnitude and direction of the lattice distortion expressed by this vector. In an edge dislocation or edge defect, the Burgers vector is strictly perpendicular to the dislocation line. It represents the distance from one step required to close a loop around the defect. Finally, motion or glide. It is the edge defect moving in response to shear stress. They move in direction parallel to the applied stress, similar to how a wrinkle moves across a rug. This movement is the fundamental process behind plastic deformation. That's all from me. I will now pass the time to screw defects. Thank you.
Hi everyone, I'm Atika. I will explain about screw dislocation. Screw dislocation is a line defect which is created when a crystal is shared so that the plates of atom are helically or spiral twisted along the dislocation line. There is no additional half plane of atoms as is the case with edge dislocation. Rather, the crystal lattice is deformed in the shape of spiral. Atoms surrounding in the dislocation line take the shape of spiral, staircase structure giving out a continuous helicoporate. Vega vector, unlike the H type, the orientation of distortion is different here. In a screw dislocation, the Vega vector is parallel to the dislocation line. This means the lattice shift occurs along axis of the defect line itself. Screw dislocation glide under shear stress and possess a special property known as cross-lift and can be moved between slip planes. This skill assists in passing dislocation cross barrier, and it aids in plastic deformation and ductile properties of metal. Thank you.
That's all from us. Thank you.